All right, let's go ahead and get started here looking at temperature and rate. So this is section 5, I believe, or is it 4? Where are we at? Section 5. Looking at how temperature affects the rate of a reaction. So as we do that, what we want to do is, hopefully you would, when you think about it, okay, when you increase the temperature of something, you would think that the reaction would increase because what's going to happen kinetically? Like what's happening to those particles when the temperature increases? You're going to see particles moving faster and with more speed, okay, with more kinetic energy, you're going to have more collisions, more contact. And more collisions means you have a greater opportunity for compounds to collide in such a way that the right orientation will appear for the product to be made. So the K value of a rate reaction or reaction rate is temperature dependent. So if you come across, a problem or a question that gives two different temperatures and you're supposed to find something related to the reaction rate, then you need to know that it's going to be more complicated. And that's why when we were talking about that insecticide that's in a lake, well, we said that the temperature, when it enters June 1st is this temperature, and the temperature stays the same, or on average is the same throughout. And so that's why that was communicated in that question that we looked at today in class. So the collision model, when you think of the collision model and a chemical reaction occurring, so bonds have to be broken, new bonds have to form, and it can only really happen if the molecules collide with each other. And in addition to that, they have to collide properly. They have to come into the correct orientation for the collision to occur, and they have to have the right amount of energy or speed for that collision, for bonds to break and new bonds to form. So there's, if you think about it, it takes a high or a number of factors to really play into a reaction occurring properly. Now, when we do reactions, we have so much material, so much, when you think of particles being so small, a mole of material is so many atoms, so many molecules, that you get a lot of collisions in the midst of the fact that it has to be the correct orientation and enough energy. So when a reaction occurs, there's always a need to have enough energy for the reaction to go forward. This is what we call the activation energy. We write it as E with a sub A, and it's the energy required to kind of get over the initial energy necessary to break bonds to get the reaction going forward. So here we have this image of this golfer at probably the worst golf course in the world with this giant bump in the middle. But so just as the ball cannot get over a hill if it does not roll up the hill with enough energy, a reaction cannot occur unless the molecules possess sufficient energy to get over the activation energy barrier. And often, once they break the activation energy, they then to finish the reaction, it's a lower energy necessary. So thinking of a reaction and kind of its coordinated diagram. So you've got this molecule of H3CNC. Okay, you've got a triple bond, you've got some things going. So for this to happen, you need, so you've got this orientation on the bottom on this graph, okay, the reactant side, you're starting there. And as energy is added to that molecule, the bond starts to bend or flex because it's getting some excess energy to kind of overcome the repulsive force of all those electrons in those bonds. And it spins, and you get to this point, the activation complex, where you're reaching the activation energy. And then it basically just continues forward, and you get this flip. Okay, because the orientation does favor the carbon-carbon bond versus the carbon-nitrogen-carbon bond. So these diagrams as a whole are called reaction coordinate diagrams, and they show the energy of the reactants and products, and therefore kind of the overall energy of the system is the difference there between the starting reactants and the products, and then you have that bump in the middle is what we call the activation energy. And that middle point, so the top of the activation energy, is what is known as the transition state. So as the molecule is changing, or when molecules are colliding together to form something new, that's a transition state up at the top at the activation energy. And the species present at the transition state is called the activated complex. So this is kind of that, some new vocab that you're just kind of working with. And the energy gap between the reactants and the activated complex is known as the activation energy barrier that you have to meet or exceed to get your products that you want. So this diagram is also in your textbook as well, but this is the idea that as temperature increases, you get more, the average kinetic energy of all of the particles in the system increases. So therefore, let's say the minimum energy needed for the reaction to occur is this dotted line. So as the temperature increases, more of the particles in that solution have the necessary activation energy to go forward, for the reaction to go forward for those particles. And so as temperature increases, you get a larger and larger portion of the whole solution that has enough energy to go forward. But at any temperature, you're going to have a full range of kinetic energies. Because remember, temperature is the average, it is a measure of the average kinetic energy. It is not the energy of all of the particles. Okay, so again, like I said, or as you can see in this diagram, as energy increases, the curve kind of flattens and broadens out through the process. Thus, at higher temperatures, a larger population of molecules has higher energy. All right, so if the dotted line represents the activation energy, then as the temperature increases, so does the fraction of molecules that can overcome the activation energy barrier. Thus, the reaction rate increases as temperature increases because more things have enough energy to meet or exceed the activation energy, and therefore that increases the rate of reaction, how many things are going to react and form the products. So this fraction of molecules can be found through this expression where R is the gas constant and T is the temperature in Kelvin. Okay, so both things that you're familiar with. So this is to find the fraction of molecules that would be found that have met the activation energy. So obviously it's based on the temperature of the reaction. And then you have the Arrhenius equation. And so this is looking at the relationship of K, so the reaction constant, and the activation energy, so how they're related. And the factor that relates them is this capital A, which is the frequency factor. And it's a number that represents the likelihood that collisions would occur with the proper orientation for a reaction. So let's say if we took the natural log of both sides of the equation, okay, so we do some natural log of both sides of the equation, we end up getting this kind of relationship where it is a, it's a line graph, right? So y equals mx plus b. So then you can use, if you want to find out the activation energy of a reaction, and you know the rate of reaction, which is K, you know A, and you know the temperature, then you can solve for M, or the slope, and solve to determine the activation energy of that reaction, which is pretty cool. So you can find K by determining experimentally at several temperatures what K is, so that it can, then use it for the temperature that you're specifically trying to figure it out at. All right, I think we wanted to stop there. Let me just double check. Yes, so we're going to stop with that, and we will obviously be working with this equation in class because, yeah, it's not necessarily an easy, obvious kind of equation to work with. So I want to make sure that we have the opportunity to kind of work with it a bit in class so that it makes more sense. Thanks, and we will see you tomorrow in class.